Example 3 is about a photon, and we're asked to calculate a number of things like frequency, wavelength, and convert the energy from electron volts to joules. So we can see in the problem we're given a photon that has an energy of 2 electron volts. So our energy, we could guess our right given, is essentially E equals 2 electron volts. And we're trying to find all sorts of things. We're asked to find the frequency, the wavelength, and then the energy in joules. Okay, so let's proceed on to solving our problem. So you're going to find, I would say maybe pause the video and just try to solve it on your own. This is fairly straightforward. But there's a lot of different ways of solving the problems. And I think the main thing that people make mistakes with is really substituting the right units in. So let's start off with just converting electron volts to joules. So if our energy is 2 electron volts and we want to convert to joules, we're just going to use dimensional analysis, where we know that 1 electron volt is equivalent to 1.6 to the power of negative 19 joules. So to convert from electron volts to joules, we want the electron volt to be on the denominator, 1 electron volt on the bottom, and then we need to put 1.6 to the power of negative 19 joules on the top. So when we do that, we can cancel out the electron volts, of course, and then we will get our answer of 1.6 times 2, which is 3.2 times 10 to the power of negative 19 joules. So that's part, I guess, first part. We found the energy in joules. Now, let's say we want to calculate the frequency. We could use E equals HF. That's Planck's equation. All right, and there's lots of ways of doing this. Or we could calculate, say, the frequency or the wavelength by using hc all over lambda. Here I've just substituted, if you know V equals F lambda or C equals F lambda, I'm just replacing, for example, the frequency with C all over lambda. Anyway, lots of ways of doing this. So let's say I just want to find the frequency. I could just use this equation and say the frequency is just energy divided by Planck's constant. Now, you have to look at your constant sheet and choose the right constant for Planck's constant. Okay, so if you look back at your notes, you could see that Planck's constant can be written this way or this way. All right, and so depending on whether your energy is in joules or in electron volts, choose the appropriate value for H. So let's suppose that I were to use the one in joules here. I can put in 3.2 times 10 to the power of negative 19 joules. And then if I'm using joules in this case, then I would use the Planck's constant that has the joules in it, which would be 6.63 times 10 to the power of negative 34 joules times seconds. I guess you could also use, let's say you didn't use the joules, you used electron volts, like 2 electron volts, then I would use this coefficient, 4.14, to the power of negative 15 electron volts seconds. So in either case, if you're plugging in the units, you should see, oh, the joules here counts out with the joules, and you'll end up with 1 over seconds, which is a hertz. Or the electron volts and electron volts here cancel out, and you get 1 over seconds. So plugging into my calculator, with either computation, I get around the same answer of 4.83. They're slightly different, and that's simply just because I'm using rounded values for Planck's constant. Okay, but you should get around 4.83 to the power of 14. So I'll put that into here. All right, so this is 4.83 to the power of 14. And this is 1 over seconds, which is the same thing as a hertz. So remember, 1 over seconds is like cycles per second. That's the same thing as a hertz. Lastly, we have the wavelength. Lots of ways of doing that. You could calculate the wavelength by using this equation. If you could see, you have E equals hc over lambda. So you could do lambda equals hc divided by E. Suppose you did that first. You could just use, we know that the speed of light is equal to f times lambda, so you could calculate the wavelength by taking the speed of light and dividing by the frequency. All right, so many different ways. Okay, so let's say I use the second way. It's 3 times 10 to the power of 8 meters per second divided by my frequency of 4.83 to the power of 14, 1 over seconds, or hertz. And we should get In my calculator, I've got 6.21 times 10 to the power of -7. And that's in meters. You could use this, by the way, hc over lambda, and divide by the energy. Let's say I use the 2 electron volts. Then now, one thing that's kind of neat is that on the formula sheet, or the constant sheet, they have hc already multiplied for you. So if you want to have it already multiplied with joules, or already multiplied with electron volts times nanometers, it makes it very, very helpful. So you don't have to multiply h times c, right, or this h times this c. It's already nicely multiplied for you. So I'm going to use the 1240 electron volts times nanometers over here. Whoops, back into my notes. Let's just scroll ahead. One more up here. And so we'll get 1240 electron volts times nanometers. This would give you 620 nanometers. Now it's a little bit different from over here. This will convert to 621 nanometers, but they're pretty close. Again, there are rounded coefficients here for our speed of light and Planck's constant and so forth. Okay, that's it for example 3. Now you can move on to the next example.